Let me see. Welcome to the embedded machine learning session. So we have three speakers, Professor Callie Howe from Georgia Tech, Professor Peipei Zhou from University of Pittsburgh, and myself, including myself from University of Pittsburgh. So three of us will talk about some of the recent works we have been working on embedded systems. So I guess first, let's welcome Professor Howe.
Thank you, Dr. Wu. Thank you very much, everyone. So my name is Callie. I'm from Georgia Tech. This is about myself, and this is what we have been doing in our lab. It's called Shark Lab. We work exactly on software hardware co-design for efficient computing. A little bit more detail that we work on domain-specific accelerators on FPGA, hardware-aware machine learning, electronic design automation. This is basically for tools. And we work intensively on graph and graph neural network. And we will welcome discussions and interesting collaborations. So for today's topic, the whole session is about software hardware co-design. This is a huge topic. And as the first speaker, I think, also because this is a tutorial, as the first speaker, I think I will cover the basics in hardware software co-design. So for those who are already familiar with somehow software hardware co-design, this may be a little boring, but I hope I can cover it in a systematic way. All right, so before we get started, let's see, what is exactly software hardware co-design? Let's use an analogy. The software, it's like baking a cake, that we're building something. And then on the hardware, it's like we're having a plate. And then software hardware co-design, it's just like putting this baked cake on this plate. So in the scenario of machine learning, this software development is deep neural network. And this hardware side here is the hardware deployment. For example, deploying on ASIC, deploying on GPU and FPGA. So using this analogy, let's go back to be more serious. What exactly do we mean by software design and hardware design in this context? So in this context, if we talk about hardware design, we are particularly interested in this automatic neural architecture search, short for NAS. This is already a very popular terminology. This is a subset of AutoML. This NAS has been very popular and it has boosted the quality and accuracy of machine learning algorithms. And here, this figure is a very, very famous and pioneer NAS work in 2018. So basically, this machine learning model is searched not by human, but by a NAS algorithm. And in this tutorial, we will introduce the major components about NAS. And then on the other side, we have hardware design. So when we are talking about hardware design in this tutorial, what are we exactly saying? We are looking for an optimized or tuned neural network implementation. Or if we talk about FPGA as the hardware, we will be designing or developing the customized DNN accelerator. And of course, on FPGA, we have more freedom, and on CPU, GPU, and NPU, we have much less freedom. So this one on FPGA is more interesting, and this is what I'm mostly interested in. So here in this figure, this is also a pioneer FPGA accelerator for deep neural network. And see, the neural network, the accelerator itself is highly customized, so it has a very high performance. So this is the hardware in our context, and this is the software in our context, and this is the hardware in our context. So being said, what are we trying to discuss today? Especially in my topic, we will answer a couple of questions. The first question, why do we need co-design? Well, I guess that's an easy one. That's why I name it as question 0. And then we have to answer this too. Question 1, how to efficiently design the software, the algorithm side. And question 2, how to design efficient hardware accelerator. And only after we understand how to design software and hardware, we can move to the third question, how can we co-design both? And here I want to especially highlight one concept, what is true co-design? And by explaining what is true co-design, I would like to present an example of a DNN and FPGA accelerator co-design that is from our past work to explain the power of a true co-design in this scenario. So this is my first tutorial that I will again, cover a lot of basics, and then we will have tutorial part 2 and part 3. Professor Zhou and Professor Hu, they will be introducing a lot more interesting and advanced techniques. So I will just lay the groundwork here, and they will introduce something more interesting. Okay, so let's take a look at co-design, different levels of co-design. If we also use this analogy from baking a cake in a cheesecake factory, what do we have? So if we are separate, if we talk about separate design, it's like, okay, now we bake a cake and then we build a plate. Well, but something can go very wrong that, okay, the cake may be too big or maybe too small. So this is completely separate design. And then for semi-co-design, what do we have? Well, it means that when we're baking the cake, we have the plate in mind that we somehow can guess how large the plate is. And then we make an estimation. Well, can my cake fit on the plate? And then we build the plate, and eventually we will have this pair. But, well, this is better, but it still can go wrong that your plate might be different from what you expected. So if happens, we still have to go back and bake the cake again. Well, what do we have best? The best scenario is a fully co-design. So fully co-design means now we're not baking the cake first and build the plate. Now we are baking and building them in pairs. So we bake a cake, and at the same time, the plate is already there. And then we bake a cake, the plate is already there. So in this scenario, we bake and build in pairs so that they always perfectly fit with each other. So this is the fully co-design, and this is what we really want. In the later of this tutorial, we will focus on this one. How do we achieve, or one example that how can we achieve this fully co-design? Okay, so this is what we have in mind. What is co-design? And now let's see the question 0. Why do we like co-design? Why do we have to implement a co-design? Well, I think the answer is pretty simple, that if we develop hardware and algorithm iteratively, we're not working together, then we may end up with this very long development cycle that sometimes the hardware developer has nothing else to do. Sometimes the algorithm developer has to wait for the hardware. And this is very tedious, very painful. So this is why we like efficient software and hardware co-design. And then the next question, how do we define efficient software design? Or in other words, how can we design the software efficiently? The first question, why do we need it to be efficient? Because if the algorithm design itself is going to take months, then there's no way for efficient co-design, right? So the foundation for efficient software hardware co-design is that we have to have an efficient algorithm design. So that's why we are interested in this automatic algorithm design approach, neural architecture search. Again, short for NAS. So how good it is? Well, early NAS, they're not that promising. You can see in early years, this NAS can take 2,000 GPU hours. This is intolerable, right? So if someone works for 6 years to come up with a good design, he or she be already fired like 3 times. But the recent NAS work has been much more efficient. Usually, I will cover later, but usually the most recent NAS work can obtain a really good DNA design in a few GPU hours. That is much, much better. And this lays a solid foundation for efficient co-design. All right, so now we understand we have to make sure the algorithm design is efficient. Now let's see what's in the co-design. What's in the efficient algorithm design? Well, what can we do? What are our choices? So this is a systematic way of introducing NAS. So just brush the background. NAS. What do we have in NAS? What are the major components? So we have 3 components. A is search space. The search space is a set of possible neural network architectures that we can consider. And the search space is usually manually designed and is huge. It can up to million. So there's no way that we can examine them one by one. And given this search space, we also have this search method. So this search method means how do we want to explore the search space based on the evaluation result? Well, there are multiple different ways. I will briefly introduce one by one that we have reinforcement learning, evolutionary search, gradient-based, and so on and so forth. And then with this search method, we also have to have an architecture evaluation. And this evaluation tells us whether a neural architecture is good or not. And usually this part is the most time-consuming part. Well, because it requires training, and we all know training is painful. Okay, so these are three major components in NAS. Now let's see, can we achieve efficient NAS in these three components? Every component has to be efficient. So the first one, NAS search space. What are our choices? There are many, many different ways to conduct NAS search. So there are many different search space. We have chain structure, for example, on this one. This is a very straightforward architecture, deep neural network architecture. And then we have this more complex search space with multiple branches and skip connection. This can be very random. And on the right side, we also have this cell-based search space. This is a cell, this is a cell, and DNA is built by stacking multiple replications of the cells. For example, this is cell 1, this is cell 2, and this is cell 1 again. So this is called cell-based search space. So this is a brief introduction about the search space. And next, remember we have the search method. So search method, there are multiple ways. The very early way is to use a reinforcement learning that we can use a recurrent neural network to predict next layer's filter size, stride, number of channels, so on and so forth, like the parameters of the neural network. And then we eventually generate a good one. Well, this is early attempt, and we see, nah, it's not that efficient back then, right? It takes 800 GPUs and may take up to a month. So this is definitely not a good candidate for us to use in efficient co-design. But don't worry, things will get better. Later, that people are investigating this evolutionary algorithm. So for example, they have the architecture, and those architecture, we can use evolution algorithm to do some mutation, to do some randomness, and we can do crossover. So this is a little bit faster than the reinforcement learning. Well, 7 days, it's a week, it's still fine, but it's not good enough. It's far from perfect. It's still not fast enough. So what else we can do? The next next revolution in NAS is that people invented this gradient-based search. So this is to apply continuous relaxation to discrete search space. So if we look at this one and this one, these are all discrete search space. But in this gradient-based search, they can relax the discrete to continuous so that we can use gradient-based search. And this is approved to be much more efficient than the previous one. So usually it can generate some result within 1 GPU day. Now it is getting much better. So as we know, we like efficient search. So this might be one of our good candidates to think of. All right, so now we covered the search space, the search method, and what about the evaluation? The evaluation is also very, very important. So using this evaluation, we have to decide which network candidate is performing well. Well, can we train the network one by one? This is, of course, the most precise way, but it can take years. And as we know, we can get fired like several times already. So what can we do? We want the evaluation to be as quickly as possible, as fast as possible. So these are different ways that people come up with for fast evaluation methods. For example, lower fidelity estimation, learning curve extrapolation, network inheritance, and especially these one-shot models and weight sharing. Well, I like this one best because it's very, very fast, very efficient. So I will give you one example. What does this weight sharing mean? This is the supernet. That the supernet compose the design space. And then for each this edges, we can choose one out of these many. So the weight sharing means, okay, this is network 1. derived from the SuperNet. And then this is network 2, derived from the SuperNet. See, they can have different connections, but these different connections all come from the SuperNet. So network 1 and network 2, if they have the same connection here, this edge and this edge, these weights are shared. And from this edge to this edge and this edge, if they have overlap, they are also sharing the weights. So this is the basic concept of weight sharing. And this is very efficient, usually within days or hours. So this weight sharing is apparently a good candidate for us to use for efficient co-design. Okay, so now we covered the basics for neural architecture search. We learned we have different ways to explore, to compose the search space. We have different search methods, and we have different ways for architecture evaluation. Which methods are suitable for software hardware co-design, especially for efficient ones? Well, I think we like cell-based. I will explain that later. Why do we like cell-based? It makes the design space simpler. And for search method, well, as long as the evaluation can be efficient, I don't care, right? We can use any method, any search method we like. But the evaluation here must be really efficient, that we like weight sharing, zero shot, or something else like estimation. Okay, so this is efficientness, that we like these choices for efficient algorithm design. Okay, so I think so far we have covered question 0 and question 1, that how can we efficiently design algorithm software. And now let's take a look at the question 2, how to design efficient hardware, meaning these accelerators. Again, I will also cover a lot of basics for this accelerator design. So what in this scenario, what are we talking about when we are referring to this hardware? Well, hardware, apparently we're interested in different accelerators. And the target platform can be CPU, GPU, whatever PU, XPU, TPU. There's so many PUs right now. Well, these are less flexible, so we don't have a lot of choice to play with the hardware. But if we're talking about FPGA and ASIC, these are more freedom, and we have more space for customization. So in this tutorial, in my part, I will mostly focus on FPGA design and ASIC design, so that we have more freedom to change the underlying hardware. So here are some examples of different architectures on FPGA or ASIC. We have NVDLA style, we have systolic array style, we can have CDNL style. These are all customizable accelerators that we can design by ourselves. All right, so what do we have? What can we consider if we want to come up with an efficient accelerator design? There are multiple levels of accelerator design on hardware, and each level can be considered with co-design. I will introduce one by one. So we have bit level optimization. For example, we have compression and pruning, and then we have this module level. Basically, we will care about how to design an efficient and high performance computing unit. And then we have this architecture level. The architecture design, is it folded or recursive or pipeline? But how do you want to design the entire architecture? So these are different levels. Let's take a look at this bit level first. So bit level, what do we have for bit level? Bit level accelerator design techniques, the most popular and efficient way is quantization. So for quantization, we can use smaller bit widths to represent original value. Well, everyone knows quantization right now. But why does quantization work for machine learning? Because DNNs are known to be robust to noise and small perturbation once it is trained. For example, I don't care whether you have 80% chance to be a cat or 75% chance to be a cat, it's still a cat. As long as we get it, it's a cat. We don't care about the exact number, right? So that's why ML algorithms are robust for quantization. And also another reason is that the weights and activations also lie in a small range, and these can be estimated beforehand. So for example, in this case, that we have a distribution and we know we know this distribution, so we can decide, hey, now I want a 6-bit, or I want a 4-bit, or even I want a 1-bit, because I know the weights beforehand already. So this is why quantization can work. Well, then the next question is, well, we know quantization. How do we do co-design? What can we do co-design here? Well, the naive way to do quantization is train a deep neural network and quantize it. So this is usually called post-training quantization. Well, this is, if we look at the right side, this is a pre-trained model, and we do post-training quantization, and then we do a calibration, we obtain this quantized model. This is done. This is done. So this is not bad, actually. This is fast, and we need few or even no training data. This is very convenient, but it may have a large accuracy loss. So this is post-quantization. This is called post-training quantization. Well, a better way here for co-design is we can apply this quantization-aware training. On the right side, quantization-aware training, that we can train the data or pre-train the data, pre-train the model, and then we keep fine-tuning it iteratively, and eventually we get a very good model. So this is slow, and it will require sufficient training data, but of course it's of much, much higher accuracy. So I would encourage you to look at this link here, that actually the quantization-aware training has been really well developed and integrated into a lot of training frameworks. So I will not go into detail here. So this is the co-design at bit level. And then we also introduced that there are 2 other levels, right? The module level and the architecture level. What are our design choice there? So at module level, the key design point is that how we want to arrange the parallelism and the data flow. Well, if you are familiar with hardware accelerator design, the parallelism is that how many computations can be done simultaneously, and the data flow means, well, how you want to fetch the data and reuse the data. So these are all very important design parameters. And these parameters has to be decided based on what workload you have, right? What does your model look like? What does your layer look like? So on the left side, this is a traditional convolution, and on the right side, this is a depth-wise convolution. So apparently they have different data paths. So this is telling us that the accelerator design, you may want to customize it based on your workload. And again, I'm bringing up this example again, that we have different architecture of a module, that you can have this type of data flow, you can have this type of data flow, you can have this type of data flow, and they all have different pros and cons. And these have to be decided based on what your workload have. Maybe you can have an analytical model, or maybe you can have a really fast synthesize that to get the real performance. But the key point is, how do we make these design choices? These design choices have to be based on your workload, and your workload is also the algorithm that we're looking for. Okay, so this is module level. And eventually we have this architecture level accelerator. This architecture level accelerator is I only give one very simple example. What are the design choices here? So we have two choices. The first is pipeline architecture, and the second is a recursive architecture. Well, this is also very well known that, for example, if you have a pipeline architecture, it means that different DNN layers will use layer-specific PEs, and for example, here, layer 1, 2, 3, and then this is different frames. So in this pipeline architecture, of course, the advantages, we have high throughput, but the disadvantages if we cannot fit deep neural networks. Well, and then on the other side, we can choose to use a recursive architecture that multiple DNN layers share or reuse the same PE, or we want to reuse, so the multiple layers can share or reuse the same PE. The good thing is it can reuse a lot of resource, but maybe it will introduce computation waste, or maybe because the P itself is just too generous. It is too general. It's too general. It may lose some efficiency, right? So generality versus efficiency, there are some trade-offs here. But again, this is just an example of two design choices at architecture level accelerator design. What can we do? Okay, so you may be wondering, we've been introduced the module level design and architecture level design, but what about co-design? We haven't touched the co-design here. How can we do a co-design at these two levels? Well, my personal opinion is a very efficient way is to do a hardware aware NAS. Well, if you already know how to do NAS, it's just a very simple extension to introduce hardware aware NAS. Well, the change is also very simple. The original NAS objective is to maximize accuracy or minimize accuracy loss. But if we want to do a hardware aware NAS, well, it's nothing fancy, but just to add another objective function, right? So we want to maximize the accuracy, and we also want to maximize the hardware performance, for example, throughput. Or you could say we want to minimize the accuracy loss and minimize the hardware performance value, for example, again, the latency, right? So this is what the easiest way, or one of the easiest way to apply hardware awareness or co-design at these two levels. Here is an example of a pioneer work for hardware awareness. So if we look at this figure, well, this figure may not be that easy to understand, but let's look at this equation. This is very straightforward and easy to understand. So on the left side, this is the optimization objective function. We call that latency aware loss. This is something we want to minimize. And on the right side, what do we have? The first term is cross entropy loss. This is the traditional classification accuracy. This is the traditional NAS objective function. And then on the right side, what do we have? We have this latency value. So by multiplying this one and this one together, we now get a latency aware loss that we want to minimize this one. So by nature, if we are optimizing this objective function, we by default is looking for a hardware friendly NAS because both terms have to be optimized. Okay, so this is hardware aware NAS example. And now so far we have introduced the bit level plus co-design, the quantization aware post-training, and module level plus co-design, and architecture level plus co-design. We can do hardware aware NAS. And by doing NAS, I can remind you that in the first half of this tutorial, we introduced a lot of efficient NAS methods, right? The gradient-based or evolutionary-based. These are all can be used to implement this, to apply this hardware awareness. Okay, so now we have covered the second question, how to design efficient hardware accelerator. And now is the most important one, how to co-design both. And what do I mean by a true co-design? Let's think about this. We have discussed the accelerator design and plus some sort of level co-design. Well, is this the best we can do? Of course, the answer is no. Otherwise, there will be no follow-up researches. Of course, this is not the best we can do. We can do much, much better than this. Well, then the question is how to apply a true co-design. Let's refresh our memory using this cheesecake factory. What is a true co-design? Here, that we want to make everything in pairs, right? We want to bake a cake and build a plate in pair. Bake a cake, make the plate in pair. This is one pair of solution. This is another pair of solution. So this is what we have in mind. This is called fully co-design. So forget about cheesecake factory. In academic terminology, what is true co-design in this context? So separate design. Separate design means we first apply a pure NAS here. This is with what we already learned. This NAS is to automatically change the network architecture. So we do a pure NAS first, and then we do accelerator design. Well, this is separate design. What about semi-co-design? Semi-co-design means we are doing the hardware search. We are doing the NAS with hardware cost in mind. What do I mean by in mind? It means that we have an accelerator evaluation in mind. that we're guessing, we're making the guess that what is the current performance of my searched architecture? Is it good? Is it bad? I have an estimation. Well, then after this, I will pass my searched deep neural network and apply accelerator design. Okay, so this is much better than the separate design because I already have something in mind. I have a rough estimation. But again, as we said, this estimation can be inaccurate. Things still can go wrong. So a full co-design means that true DNN accelerated co-design requires that everything is designed in pairs here, right? We have one deep neural network, one accelerator. Okay, I'm not happy. That's fine. Let's keep doing. We change the architecture a little bit and we change the accelerator a little bit. Okay, I'm still not happy. That's fine. Let's keep doing. I keep changing the architecture and I keep changing the accelerator. And eventually, when I'm happy, I already have the output is already a searched deep neural network with an accelerator. And then the next step is we only need to do a fine tuning. We do not need to design everything from scratch because we already have this design in pairs. Everything is already made or built. Okay, so this is the idea of fully co-design. And this is what we want in mind, ideally. So ideally, we want to have a co-design engine sitting here, and then the solutions are generated in pairs. The solution pair one DNN, one implementation, or one accelerator. Solution pair two, one DNN, one accelerator. And then so on and so forth, solution pair n. So for each solution pair, you can have different objectives. For example, for solution one, you wanted to accuracy achieve more than 90%, but the latency can be 10 frames per second. And then for solution pair two, you want the frame rate to be 30 frames per second, but the accuracy can be 85%. So this is the trade-off. And by having this co-design engine, the beauty is we can generate different solution pairs with different objectives, with different performance requirements. Okay, so this is what we have in mind, ideally. Well, then the next question, what does this co-design engine do? This co-design engine apparently is sitting in the middle. Well, let's look for something in the middle. That this something in the middle must be very, very important and will be the key to find both DNN and implementation. All right, so finally, I will introduce an example of FPGA DNN co-design that is implementing this true design engine that the solutions are generated in pairs. All right, so in the next 5 minutes, I will briefly talk about this piece of work. This is from 3 years ago. So what have we learned so far? We have learned about NAS that, okay, we can use this cell-based search space because cell-based is very easy to implement, that we have one cell, we just stack it by multiple times, and then all of a sudden we get a good DNN. And now what we learned about accelerator? Well, based on what we learned, we know that accelerators are composed on basic processing elements. Well, for example, you have this underlying accelerator, you have convolution, you have depth-wise convolution, and you have another convolution with different size. So this is your underlying accelerator. Now here comes the question. We have NAS, we have accelerator. How can we find this something in the middle? That is very important. Here, this is something in the middle that is very important that can decide both. Decide both the NAS, decide both the DNN and the accelerator. Well, this is something interesting. We observe that, okay, the NAS is cell-based, and then the accelerator is processing element-based. Well, now we are very happy because the PE, the processing element, can implement the basic blocks, meaning these cells, right? So now we have built the connection. Well, accelerator PE is implementing this cell. So this is something in the middle that we're looking for. As long as we know what's the cell, or as long as we know what's the PE, then we're all good. we can solve, or we can find the best architecture, the best DNN and the accelerator at the same time. Okay, so what is this something in the middle, and how can we look for it? This is an illustration that how this important basic building block sitting in the middle can decide both parties. So this is one example. Suppose the cell looks like this: 4 layers, different combination, different number of channels, and we use this cell, we stack it or repeat it by a couple of times. Then all of a sudden we have a very good deep neural network. And then for this, each block look like this, right? This is a basic cell. Well, this is how the basic cell can be used to decide the DNN architecture. What about the implementation? Well, the implementation is also very simple. Because we have this PE, we know the standard cell, and it's replicated a couple of times. Well, why don't we just implement this PE, use this PE to implement this standard cell? So this is the implementation for one standard cell, or for one cell. And this one will perfectly implement one replication. And then the other replications, there's no surprise. We're just reusing the same piece of hardware repeatedly because the computation doesn't change, right? So this is very, very beautiful. So as long as we find this something in the middle, all of a sudden we can decide architecture and we can decide the accelerator. So everything is perfect. Now, the question is, because this is so important, how can we choose these basic building blocks from a large design space? Now the key becomes, well, if this is so important, its quality must be crucial. Well, yes, of course, we have to choose a very good, this basic building block. Then how do we do that? Okay, so very briefly, how can we do that? We have a 3-step approach. So if we look at the right side, this is not, if we look at right side, this is just an auto HLS, high-level synthesis generator, that during the search, I don't want to write accelerator by myself. I want to write a template, and then the computer is generating that for me. Right? So that's why we have this auto HLS generator, accelerator generator. The output of this one will be a hardware FPGA accelerator. Well, enabled by this one, let's take a look at the left side. The left side is the code search engine. Well, we have 3 steps. Let me give you an analogy. These 3 steps is just like a job interview. Well, you cannot expect that you will go on-site interview at the first shot, right? So typically, well, the HRs will do a CV screening, and then they will filter out some candidates, and then they will do a phone interview, and then they will pick up some promising candidates again and invite them for on-site interview. So this is exactly the same what we're doing here. So we have 3 steps, and for each step, we're filtering out some unpromising candidates so that we don't have to deal with the huge design space. Okay, so for the first step, we're doing this performance estimation. We know how large the building block is, how small the building block is. Is it too large? Is it too small? And we do a very rough pre-selection on the first step. And then on the second step, we do a building block selection. We only keep promising ones to reduce the design space. And this is the Pareto curve that we draw. I will skip the detail, but well, of course, if we have multiple candidates, we only care about these that are on the Pareto curve. Well, now on the second step, we filter out some, and then in the third step, we can finally have a detailed evaluation. We can perturb, we can train, and we can select these DNNs within performance constraint. And because we have this auto HLS generator, we know this is an accelerator template, and we can, during the search, we can just automatically generate this HLS code. So we don't need to write on our own. Okay, so let me skip all those details. Let's see, co-design is actually very, very good, very practical in real world. So we've been participating in this DAC design competition that This is a object detection algorithm or acceleration on FPGA and GPU. Let's see how we did. In 2018, we won the 3rd place. Well, it's not bad, but we're not quite happy about it because it was really painful because we were independently designing this DNN and FPGA accelerator. That was a lot of iteration and it took a lot of time. Well, then in 2019, we learned this co-design technique and see all of a sudden we got this double championship for both FPGA and GPU. So we're gonna say that co-design is really, really effective and it leads us to the victory. So co-design is really has its power. Okay, so this is the summary of my part that we learned why we like co-design, because it's fast and it's of high quality. And how do we efficiently design software algorithm? Well, we learned neural architecture search today. And the question 2, how to design efficient hardware accelerator. We learned there are multiple levels of optimizations. We have bit level, we have module level, and we have architecture level. And finally, the most important question, how to co-design both and what is a true co-design, that we hope the algorithm and accelerator can be searched in pairs. And we briefly introduced an example of deep neural network and FPGA accelerator co-design. And eventually, finally, I realized that I was about to talk about this autonomous system, but I didn't put too much in the slides. So this is just one overview that if you're interested, I can share with you more details, or I can share you with a more detailed slide. So in autonomous system, why do we like co-design, or why do we need a co-design? Because in autonomous system, that things are getting much, much more complicated, both from the model side and from the hardware side. So from the model side, what are we looking at? We are looking at this multimodal, multitask learning. For example, in autonomous cars, you will have LiDAR input, image input, and ultrasonic input. And you have multiple tasks, lane detection, pedestrian detection, and traffic sign detection. So the model is becoming much, much more complicated. That's the model side. And then on the hardware side, for autonomous system, the system is very, very heterogeneous, right? So we can have CPUs on the platform, we can have GPUs on the platform, we can have FPGAs on the platform, and we also have different controllers. So how to efficiently mapping the MMT, this multimodal, multitask model on the heterogeneous platform, it itself is very complicated. And how to search a good MMT model based on the platform you have is also very complicated. So this is exactly the best use case for software hardware co-design for MMT on heterogeneous platform, especially for this autonomous driving and autonomous systems. So again, I didn't put too much detail for this slide, but if you're interested, please email me and we can share more information later. Okay, so finally, this is our lab, and we work for software hardware co-design for intelligence and efficiency, and this is my email, and this is our homepage. And if you have any questions or suggestions, please feel free to email us or visit us in person. All right, and this is the reference. So I think I'm done for my part. All right, so I think maybe I should open for questions, or I can pass to my next speaker. Well, I guess it's hard to ask questions remotely. So I think maybe we can welcome the next speaker, and then if we have questions, we can type in the chat box. I guess that will make things easier.
Okay, thanks. Thanks, Callie. Okay. Okay, there's one question, Callie. You want to address this one before I start?
Oh, okay. Let me take a look. Can you shed some light on underlying communication architecture for co-design? Oh, that is a good question. So I think the question is, how can we consider communication for co-design? The communication. So eventually the co-design will boil down to how to design the objective function, the loss function. So for example, in the co-design that we have, let me start my video. So if I have a co-design engine, eventually we're minimizing this the algorithm, the accuracy and the hardware performance. The hardware performance can involve everything you want, right? It can be latency, it can be throughput, and if you want to emphasize on communication, then of course it's about how to model the hardware, including the communication cost. So if you have a very precise hardware performance model, then just throw it in the objective function. The objective function will automatically help you to reduce that part of the cost. Well, that's one way. And then the other way is we also have a related work that we explicitly take care of the mapping from the algorithm to the hardware that is communication aware. So another way of doing this co-design is you have to find a way to do the one direction first, right? Without co-design, we have to think that how to design from the algorithm mapping to the hardware that is communication aware, that we know how to optimize the communication already. And then on top of that, we can start to think from bottom up that how can we design an efficient algorithm. So to summarize two key points. First is we can have a very accurate objective function that is considering the communication loss. That is a very good question. And then the second direction is, okay, I just take the the top-down approach. I only have to understand how to do the perfect mapping or implementation with communication awareness. And then I will go back and think, how can we change the algorithm that makes it more communication aware to reduce, for example, you realize, okay, in my system, this is the communication bottleneck. Well, can I change the algorithm that let me reduce this part a little bit to distribute the communication to somewhere else? So that is also another idea of doing this co-design. I hope that addressed this question. At least I'm just giving some random thoughts. I guess I will give the stage back to Dr. Zhou. Sir, please go ahead, Dr. Zhou.
Thanks. Okay, so probably we can collect all those questions, and then after this tutorial, all the speakers have been given the tutorial, so we can address all of them. Thank you, everyone. So this is Peipei. Today I'm going to introduce the practice on performance auto-tuning in AI compute chip. I think that this is some experience that I have during my industry experience. A little background of myself: I joined the University of Pittsburgh CE department last September, and before that, I spent 7 years at UCLA, obtaining my PhD in doing customized computer architecture design and programming abstraction. And after I obtained my PhD degree, actually I went back to China to work in an AI chip startup company in Shanghai there for 2 years. So I brought up 2 generations of AI ASIC chips in Shanghai in Flame technology. And there I basically do the pre-silicon modeling and post-silicon performance auto-tuning. So here, actually, this talk will be mainly about my experience there and also some of my reflections, which shed light on my current research. And my current research basically can be summarized as 3A, the architecture, abstraction, and also application. I mainly focus on the computer architecture design for FPGA, AI, ASIC, GPU, and something like neuromorphic computing as well. And the abstraction is like how we can build the compilation support for customized computing to ease the programming of these devices. And applications including artificial intelligence and genome pipelining, health applications, and the different kinds of wide domains of applications. And so here you probably see some of these platforms that I've been extensively working on. This is one of the most currently the Heterogeneous SoC platform provided by Xilinx, and also NVIDIA like a mobile GPU platform. So these are some of the platforms that my students and I are currently working on. And here's my research website, and you're more than welcome to find more information there and reach out to me through email. Okay, so why we need this AI customized chip? So as the AI training increased, the model size increased actually faster than Moore's law. So if you see the change of this model size in billions of parameters in this chart, you will see the AI models basically double almost, or I would say the double in every 3 months. So the size easily gets 10x in just 1 year, and that speed is much faster than the Moore's law. And without this customized ASIC chip to build high energy efficient circuits for these models, we cannot even train these models in a reasonable time. For example, if we want to train this GPT-3, now it's really costs more than $1 million. So that's a huge thing. And the customized chips actually help reduce the cost and also help reduce the power and energy we spend on training these chips, in training these models. So here I list some of the AI ASICs or popular AI ASICs that I think worthwhile to take a closer look at. So 2 of them are actually from NVIDIA. That's NVIDIA V100 and NVIDIA A100. And these 2 generations of GPU provides very high peak performance in both FP32, that is the floating point 32-bit IEEE standard, but they also provide extreme high throughput for the mixed precision data types, including the TF32 and the BF16. And in terms of the chip memory, these architectures, they are featured with almost like 20 megabytes to 40 megabytes on chip memory. And in terms of the off-chip bandwidth, they are very high. So nowadays, almost all of the data center AI ASICs, they have HBM stack within SoC. So they use the 2.5D interposer techniques to stack these HBM high bandwidth memory together with this SoC. And if you see the layout of the chip, actually you can view this HBM chips, they are coupled with this SoC chip, either from the left to the right or to the top to the bottom. And if we take a closer look at this transistor count, they are actually very huge. So from like V100, it contains 21 billion transistors. And for A100, it contains like 54 billion transistors. And I listed I listed 2 generations of the AI ASIC chips that I have been working in Flame in the right part. So compared to NVIDIA, actually these 2 ASIC chips, they have a very similar teraflop in terms in floating point 32-bit and also in TF32, and they have very comparable off-chip DRAM bandwidth and also the area and also the transistor count. So the question is that after these 2 years of experience in bringing up this AI ASIC, what I can share and to the AI research community, right? So I think that's something that I want to share for today's tutorial. That's how we build this AI SoC in terms of this hardware and software co-design view. In doing that, we first need to get a glimpse of the SoC or the current mainstream SoC for AI ASIC, and also how we build on top of that to build the whole stack of software compilation framework. And after these 2, we can kind of learn how we do this auto-tuning or automatic performance tuning framework on top of this software stack. So let's first take a look at the NVIDIA V100. So this is actually a schematic of the overall architecture. So NVIDIA V100 has 84 streaming multiprocessor units, and within each streaming multiprocessor unit, they have the core for FP32 and also for FP16 and also FP64. So before A100, actually V100, they only have this streaming multiprocessor, and within each streaming multiprocessor unit, the hardware resources, they can reconfigure or they can take some instructions to be configured to compute either floating point 64, floating point 32, or floating point 16. And they have 4 HBM stacks, which is shown here, 1, 2, 3, 4. And they give us the highest 900 gigabytes per second of chip bandwidth. And what's the biggest change between V100 versus V100? Let's take a very quick change. So if you only see the schematic, they don't have much difference. So very similar architecture, but with a higher number of streaming multiprocessors. So in terms of the 80 something, now we have 128, and very similar like architecture, which is like off-chip or HBM stack, the from left and also from right. And the biggest difference actually lie within this streaming multiprocessor unit. So let's take a look at this the thing. So if we zoom in with this streaming multiprocessor, we have this integer and floating point and the tensor core unit. So what are these? You can think of these as a customized compute unit within the ASIC. If we build something which can accelerate both integer and floating point 32 and floating point 64, we actually lose some of this flexibility when we configure these bits, because we need more bits in controlling these hardware resources. And in order to overcome this, some of hardware vendors, they will pick the most commonly used data types and put specialized hardware for it. For example, for tensor core, that's one of the things, I think the architecture contribution which has been introduced in AI ASIC core this year is that we build a very customized tensor core unit just to accelerate certain types of data. For example, here in this case, that's floating point 16. Because floating point 16, they provide higher like computation T-flops and the higher integration intensity compared to floating point 32, but maintains the similar like training accuracy in most deep learning models. If we take if we also view as a floating point 32, we know we have like an 8-bit exponent part and 23-bit of a mantissa part, and for the floating point 16, they have 5 bits of exponent part and only 8 bits of this mantissa part. So they have a different distribution, but FP16 still give a very good accuracy or the training performance. So that's good, and that's why we adopted this new tensor core unit within this ASIC core, just to accelerate these type of this data type, and provides extreme high computation intensity. And all these tensor cores, they are nothing but matrix multiply units. So they support different shapes of matrix multiply unit. So this part is an example of the tensor core, how tensor core support 4x4x4 matrix multiply within one instruction. So you can think of it as each clock cycle we can get 64 Mach unit computation within this tensor core. So that's a very high intensity unit. And for A100, they upgraded this tensor core so that it can accelerate 8 times 4 times 8. So it basically provides 4x higher computation intensity compared to a V100. So that's the biggest thing we have observed since V100 GPU generation. So they have a specialized tensor core unit, and then we can do this with much higher throughput and under the same power budget like the TDP, the thermal design power. And so that's when it goes to the in-flame AI ASIC, which I have been working on for 2 years. If you just look at this, like the card is almost the same because they are all like PCIe standard. We put these 2U PCIe cards together and then to put them in an accelerator pod in a single server. So we can do this distributed computing within a single data server. And if we pile the servers up in the data center, we can easily scale out the distributed training to 100 or to 512 cards for a single very large deep neural network model. And this is the second generation. We have this second 2.0 SoC, and in this right figure, we show that how we put these 8 cards within the data center. And for the communication part, we have the ESL link to provide the high board-to-board communication. So this ESL link provides us with a 600 gigabytes per second board-to-board communication interconnect. And we basically build on top of this pod design and then scale out the distributed training process to large amounts of servers. And so I want to give some introduction to the architecture details of the DTU 1.0. That's the Inflame first generation of AI ASIC chip. So these slides, actually, they are public available. This is published in 2020 AI conference called Hot Chips. So in the Hot Chips 2020, we introduced the details of this design in terms of the SoC. So DTU first generation DTU is built on top of 12 nanometer FinFET global foundry technique. And we have in total 14 billion transistor, which provides us 20 teraflops for floating point 32, 80 teraflops for floating point 16, and 80 teraflops for BF16. So you might ask, what's the difference between BF16 and FP16? The difference is that floating point 16 has less exponent bits than BF16. So BF16 still has 8 bits exponent part. So it has the same range as FP32, but with less accuracy. Why we need this new data type? That's because if we observe or as the deep neural network models, they become deeper, and we have to do more and more accumulations of the data. So we call for a new data type that can represent higher range of floating point data. So FP16, in some cases, we cannot converge by using FP16. So we need to use BF16 to still enable the high ranges of floating point data while still compacting the data type to 16 bits. So that's the difference between floating point 16 and BF16. And for convolution neural networks or these MLP, matrix multiply operators in your network, we always adopt like a BF16. And for other operators within a neural network, for example, the batch normalization or linear normalization, actually we use FP32. So that's a mixed precision training in a neural network model to guarantee the convergence of the deep neural network model. And this is an overview of the SoC architecture. So in total, we have 32 AI compute core in 4 clusters. So in each cluster, we have 8 AI compute core. And we have 40 data transfer engines. So these 40 data transfer engines, some of them, they are actually cluster data transfer unit, and some of them, they are called local core data transfer engines. So you can think of it as some global DMA or local DMA. And these DMAs are used to transfer the data from the off-chip HBM memory to the on-chip local buffer L2 cache and L1 cache. And the 2 HBM stack providing total 512 gigabytes of chip bandwidth. And for this tensor ALU core, that's actually it's based on the VLIW instruction set, so very long instruction word, and we can issue the matrix multiply within certain shapes, which I will cover in the later slides, within single instruction. So by issuing fully pipelined instructions within this tensor ALU kernel, we can do fully pipelined matrix multiply computations within single tensor core. So that's a key to achieve high computation intensity within the AI ASIC core. So in terms of this performance spec, we can support different data types, including floating point 32, floating point 16, BF16, integer 32, integer 16, and integer 8. In that sense, we can also use the same training AI ASIC chip to accelerate the inference stage as well. Okay, so if we zoom in within this tensor general core, we can think it as a hierarchy architecture. So we have this modules to bring this data from this L2 cache to L1 cache, but we also have the shared or we call the scalar register and vector register, which we can store the temporary data within a single core. And the vector registers we have these instructions to directly access the vector register to do this matrix size or matrix shape computation. So if we do see this tensor shape instruction, we support that can be summarized here. So in terms of the floating point 32, we can do either a 32 by 1 by 8 matrix multiply or 16 by 1 by 16. But in total, within one single instruction, we can do 256 MAC operations in single cycle. And for floating point 16, that's actually higher. So floating point 16, we can compute 64 by 4 by 4 in total. That gives us 1,024 MAC operation within single cycle. So that's basically 4x compared to floating point 32. And that gives us a lot of flexibility because we support different tensor shapes. In that sense, we can accelerate different kinds or different shapes of convolution neural network operators or matrix multiply operators by composing different types of instructions together within a single core computation. So that's a key. We can, as we provide a flexible computation shape, we can accelerate flexible shapes of operators without losing or without wasting any computation resources. So that's how we basically tackle this CNN or matrix multiply within this AI ASIC core. So we can compose them in different shapes, like in this way, very tall matrix, or like in this way, in this square matrix multiplication. So these are some more examples of different shapes of matrix multiply instructions we supported within a single cycle computation. Because in this SoC design, we adopted the scratchpad memory design. In that sense, the users or the programs have full flexibility in managing the data within the chip. So we have the L2 shared on-chip buffer and the L1 local on-chip buffer. And if we see this in a memory hierarchy, we first bring the data from the off-chip HBM stack to the L2 shared cache. And then we bring the data from the L2 cache to the L1 cache, and from the L1 to L0 register file, we use instructions to load the data in to do the computation. And as we get closer to the local register file or get closer to the tensor ALU kernel, the interconnect the bandwidth increase. For example, from L1 to L0, the on-chip bandwidth can be as high as 10 terabytes data to sustain the computation of this tensor ALU kernel. And in order to tackle the challenges within the AI model, which we have different kinds of the DMA operations, we have to provide a very flexible DMA operation, hardened. Actually, these DMA operations, they are hardened in the circuits. So the circuits can support different types of the tensor operation in DMA, in data transfer. These include the slice and deslice. So slice is that we pick a piece of the submatrix out of the large matrix, and the deslice is vice versa. So we put back of the small matrix back to a large matrix. And the reshape or padding or concatenation, broadcast, and downsampling, and the constant filling and the mirroring. So these are the flexibility we provide as in the DMA itself. And some other things. Okay, so this one is the actually a schematic of the how we do this reshape to change the layout of a tensor. So after we have these programmable DMA and the programmable compute kernels to do different data types and with the different matrix shapes, how we compose them together to work on an AI training model. So that's how we build these AI models, build the AI software stacks from the AI models to kernels. So when we have these models, usually they're described in a graph manner. For example, HO graph is the graph in TensorFlow, or in PyTorch we have, or JAX, we have a different description format for the graph. But after we get the graph, we got the operators, which sometimes we call these composite operators as a complex operator. And within the complex operator, they are composed of the small atomic operators. And then for each atomic operator, we need to figure out how we bring the data to the chip and how we compute the data after we have the data on chip. So that's the high-level idea of how we do this AI software stack compilation. I don't show the details about the kernel fusion or some other model optimization techniques here, but this is just a high-level idea of how we map the models with described as a graph to a single kernel computation. And this is an example of the TensorFlow code to show a computation graph. So we have the input data tensor X chain, and another one is the W, which is a kernel or the weight. And we have to multiply them together, add it by a bounce, and then subtracted that with the target, and then get the loss that we need to do this backpropagation. So we describe this in the TensorFlow as using the PyTorch, as the Python high-level languages. And then after we get this computation graph, for example, this is just a simple graph, but so most of these computation graph for machine learning models, they are huge. So this one is like a ResNet 50 machine learning model computation graph. So they have 50 layers of convolution, and we have this is just a picture to show the different block, and within different blocks we have different numbers of ResNet, different numbers of convolution layer, and also the batch normalization. So that's for within this each node we have the detailed description of the computation shape. For example, if we see here, we have detailed information about the first layer of this res2b branch 2b convolution. So the output channel number is 64. The input kernel size is 3, so that it takes like 3 by 3 convolution, and the input channel size or the input height and width are all listed here. So these are the detailed operator information that we can get when we compile the machine learning model. So after we get all this shape information of the machine learning model, we need to compile these operators and get the code that runs the highest performance for each shape. So that's one solution. Another solution is that we just develop a general convolution kernel. So whatever the shape it is, we just compile the kernel within. We just compile the convolution on that single general design. So there are pros and cons. So the general convolution kernel is fast. So after you develop the code, for example, within a software team, we can hire 1 people to develop this general kernel design and then finish that in a month. So that that's it, right? But the downside is that that does not sustain the computation throughput. So that does not meet the highest performance requirement as we require when we do for example, we want to beat the machine learning ML perf performance when comparing to another device. So we need some of this customization, or let's say the high performance convolution kernel for different shapes of convolution. So that's very important, and that's a key to achieve the very high performance throughput in this AI ASIC. And but before we go into that detail, also emphasize some of the challenges that the training compared to inference. So the biggest challenge of AI training is that the memory usage is very high. So when we talked about the AI inferences, so even though we have like a very deep model, but the data we need to keep within a single chip is just one layer. That is the layer that you're currently computing. However, in the AI training models, we cannot release the memory usage until we goes back to this backpropagation stage. In that sense, we keep all this memory data or the temporary data as we do this inference stage. So the memory usage becomes higher and higher, and then it achieves like a peak memory usage right before we do this back propagation. And that's the biggest challenge of the AI training. So we need a large like storage space, and we needed to do this temporary buffer allocation and management. And also we need to do careful scheduling. So that's the challenges of the AI training compared to AI inference. And usually when we design this AI software stack for customized hardware, we usually put our code or the AI software codes with the interface or the input of the software stack into the graph level. So here we show that in the test flow, the graph level is within this XLA. That's the accelerated linear algebra part. So that's the input or the first layer of our AI software stack. But after that, actually we'll build these different levels of compilation to compile the graph to different operators, and from the different operators we generate the code for the DMA, and we generate code for the computation kernel. And you can see we have so many different types of the XLA operators. So some of them, they are just the DMA only operators. Some of them, they are computation intensive kernels. For example, here, this is a dot, this is a convolution. So these two are the top two most time consuming kernels within the AI model. And for the other, they are also some of these computation intensive kernels, like the batch normalization inference and batch normalization gradient. And okay, so from the graph scheduling to the AI kernel, actually that's a very popular scheduling algorithm that's being widely adopted or studied in EDA field already. So we can easily compile this graph or DAG directly acyclic graph to the scheduling scheme within our chip. So this algorithm part, I think we just use or reuse the most current state-of-the-art scheduling algorithm. But in terms of the algorithm or the convolution or dot computation part, that's the I think that's the mystery part or the key part for each hardware vendors. So here, before we jump into how we do that, this is a show of this convolution computation. We have a like sliding window. For example, here we show this 3x3 sliding window, and for this image, we have a large like height and width image, and we just slide these kernels on top of these images, and then accumulate the data within this sliding window to be the new output data. So that's the 2D convolution. And for 2D convolution, as you can see, we have this huge data reuse when we slide the data. We need to adopt this kind of data reuse or optimization techniques within the data our computation kernel as well. So that's how we first save the off-chip bandwidth, but just optimizing or increasing the data reuse within the single kernel. Okay, so this is this operator implementation flow of how we bring the data from this host memory to the L3 off-chip bandwidth, and then to this L2 shared cluster memory, and to the L1 local memory. So these data transferred are completed by this DMA, by the customized, or we said programmable DMA. And for this computation kernel, it is responsible to bring the data from these L0 register files to the Mac computation kernel. So with this DMA, that brings the data from the host memory to the L1 memory, and with this SIP or this computation kernel to read the data from the L1 data to L0, we can finish the whole operator computation. So here is like a trace, or we said let's say this is we show this SIP DMA, that's the local DMA, and this is a SIP, which is a computation kernel. And here's the DMA to transfer the data from this L3 to L1, and then this is where we do this computation within the within the compute cores. So here, all these SIP DMA, they are overlapped with the computation with the SIP, because we adopted the PMO buffer strategy, so that the computation and the DMA transfer, they are overlapped, and then to improve the efficiency of the computation. Okay, so from the AI model to kernel part, for example, the models part with the input is the input is like the different kinds of AI deep neural network models, like including ResNet, XNet, GoogleNet, or STM model. And then in the graph level, we can do this operator fusion or scheduling optimization. And in the operator part, that's where we have the different shapes of different kinds of operators, and then compile them into different kinds of data transfer instructions and the kernel assembling instructions. And within the kernel instructions, we leverage the instruction pipeline and the loop unrolling or registry naming techniques to increase the pipeline efficiency within the single core. Okay. And how we can do this in an automatic way, or can we build an auto-tuning framework to generate the high-performance convolutional neural network kernels for a customized AI ASIC? The answer is yes. So, and the key is that we needed to do this automatic code generation for both the DMA part and also the computation part. And for the DMA part, we want to build a high-level data flow synthesis framework to compile the convolution kernels into different kinds of data flow or different kinds of data transfer schemes. And for the programmable computation kernel, that's where we adopt the JIT, that's just-in-time assembly code generations, to generate the high efficiency, to generate high efficient kernel codes when given a certain shape of computation, convolution computation. So that's how we lay the foundation of this automation. And after we have these two automatic code generations, we can leverage the design space exploration to do or to search all the available schemes or data flow schemes in the runtime, and then pick up the best one that achieves the highest throughput, the lowest latency, and then use that generated code as our production code. Okay, so in order to design this high-level data flow synthesis, we first identify the input and output and the configuration and the constraint of the framework, of the optimization framework. Basically, we want to use a systematic way and automatic way to optimize a data flow synthesis framework in a systematic optimization way. So the input is the shape. So whenever we need this optimization, we need to give this exact shape of this convolutional kernel. And the output is the schedules with the tile shapes in the L2 and L1 and the corresponding DMA configurations. So say that we have to compute a 56 by 56 convolution with the input channel S3 and output channel S64 and the 7 by 7 kernel width and kernel height. This is the input, or this is the convolution shape we need to put or give to this data flow synthesis. And the output is the tile shapes that we need to cut these input feature maps into small tiles, and how or where we put these tiles within this parallel unit. So that's the output. And within valid scheduling, we need to consider the different hardware constraints, including the L2 size, the L1 size, and the parallel strategy, and also the prefetch strategy. For example, whether we use PMO buffer, or whether how we share this, or how we do the parallelism. So we have the feature map, we also have the kernel, and then we can either parallel on the feature map and duplicate the filter, or we parallel on the filter part, but we duplicate on the feature. So these are different parallel strategies we need to consider in our framework. So that's a huge design space exploration part, and we build these hierarchies of design space exploration within our framework. So we first initialize the tuning parameters. So that's just to list all the valid parameters for each step. And then we generate a huge design space in the certain steps. And then based on whether this design point fits on chip or whether it fits on this hardware constraints, we can prune this design space by considering the hardware constraint first, and then by considering the feature size constraint, and also some other heuristic. And then we can gradually reduce these design spaces to a reasonable size. So within this reduced design spaces, we can generate the code in the runtime and then all execute them in the real silicon, and then measure the runtime and collect the best one out of the 100 of valid solutions, and then use that one as a production code. So that's that's the general flow of the data flow synthesis. And also we define the domain-specific language support to facilitate that. So here I show a high-level idea of what's this domain-specific language looks like. So here that's this convolutional shape where we have this input shape. Sorry, we have this L3 shape. So that's the shape, the original convolutional shape we need to do the computation. But here we also show extra 2 lines. So these 2 lines are the shapes that we bring the data to the L2 buffer, and also the data we bring into the L1 buffer. And with this shape, we actually describe the data flow already. And then the underlying compilation framework will take this kind of DSL description and then generate the corresponding DMA or control flow, and the data flow to hide these details of this data flow. So as a DSA part, we abstract all those compilation away. We just define the shape, and then the compilation framework will compile this data flow scheme based on this shape to the corresponding DMA operations. So, and this is some of this intermediate code we have. So if we have the shape as described as in the previous slide, then this code will actually bring the data here from the HBM to this L2 buffer, and from these 2 lines are bring the data from the L2 buffer to the L1 buffer. And here is that we do this computation, and then we have some of this parallelism strategies specified here. And after the computation, we need to do the D-slice, or we bring the data from this L1 to L2, and then from L2 to L3. So these are the intermediate DSL code we have. And in terms of this computation or convolutional kernel code, since I cannot show the exact kernel code, but I show something instead, that's the VLW code example from Xilinx. So I would just do some illustration for purpose. This is not the code we have due to the privacy issue, but you can get a glimpse that within each VLW instruction, we have some load instruction and store instruction. We also have these vector computation operation. So by fully pipelining these instructions, we can have a very highly efficient computation kernel. And this automatic code generation is actually enables to generate generate code for any types of convolution kernels instantly. So I would say that this is a huge time saver within our software compilation stack. And also we explore different kinds of this parallel strategies. So whether we do this parallelism on this feature map, or parallelize this on weight, or we parallelize these the other like data within the computation. So we specify, or we identify most commonly used data flow as templates, and then we generate these DSL for each template, so that we can compile the DMA operations for each template automatically. So this one I have I've shown the design space exploration in using this framework. So the different colors actually shows the different steps, the design spaces after each step. So initially we have a huge design spaces as 10 to the power 22 or 10 to the power 26 different data flow schemes. And after the pruning based on the hardware constraint or based on some heuristic shape consideration, we can gradually reduce these huge design spaces to just a few hundred, less than 100. And then we can explore all these different data flow automatically by generating the code first and then execute them on the real ASICs and then evaluate the performance of each data flow, and then we can get the optimal solution. So by using these methods, actually we can generate the code, very good performance code, and beats the manually written convolutional kernel code. So we have some like experiment results here. So compared to hand-tuned code, which, for example, for the Resident 50 inference, that's the forward parts, the hand-tuned convolution kernels previously developed by software engineers within like a group of 7 people developed for some amount of time. They have achieved like 91 microsecond. But by adopting these automatic framework, we can achieve this in 66 microsecond. And then for BPI, that's a backpropagation inference stage. The hand-tuned gives us 150 microsecond, while the automatic codes generates like in 70 microsecond. And for the backpropagation kernel, we beat the hand-tuned kernels by almost like 3x. So that's a very impressive and very huge improvement compared to hand-tuned code. Not only to say that it saves a lot on the human efforts and saves the cost in the engineering cost. So I think this is all I have for today. And then I hope that gives some of your thoughts on the experience on industry level automatic performance auto tuning in ASIC chip. And so if you have any questions, feel free to put that in the chat message or email me. And that's all. Thank you.
All right, thanks, Peipei. And next, I'm going to present some of my recent research work named Towards Independent On-Device AI, Inference Without Battery and Learning Without Label. So there are 2 parts of my talk. The first part is about inference, and the second part is about learning. All right, so the first slide is just like quick introduction of AI comes in all sizes and shapes in many different application domains: agriculture, military, power system, manufacture, education, medical operations, and finance. And this figure shows the current computer device landscape. So on the right-hand side, we have all these cloud servers, and then we have these edge servers. And on the more left-hand side, it's more related to the devices that we are concerned about, like drones, smartphones, AR, VR devices. And then if we push this further to the left-hand side, we have like RFID tags, robotic intersects, swallowable capsular or backscattering devices. So in this talk, I'm trying to answer 2 questions. So the first question is that, can we power small deep neural network models with ambient energy? So by ambient energy, I mean the energy that we can harvest from the environment, like solar panel, and like kinetic energy, thermal vibration, stuff like that. And this question is important because there are a lot of applications that needs this kind of needs this kind of working environment. For example, like in hard to reach areas where that in on the water, under the bridge, in harsher environments, for example, in the battlefield, in the space, um, and used for wild animal monitoring, agriculture monitoring, um, volcano and wildfire monitoring. So in all these kind of scenarios, there is a need that we need to deploy these sensors onto places that hard to reach and hard to, which means that hard to replace the battery. So how can we use energy harvested from the environment to power these systems? Right. So the second question I'm trying to answer is that can we can these DN models learn without labels? So we know that like nowadays how we are what we are doing is that we usually train a deep neural network model in the server, and then we deploy the model onto the systems. But many times we actually need to adapt these models, for example, in order to do transfer learning, personalization, or adapt it to different domains. And if we want to like modify the model or train the model, if we are using supervised training method, then we need to constantly asking for a label, which is annoying. And many times the domain expertise is needed to do the labeling. For example, if it's a medical application, then we need a doctor to constantly label the new data, which is not really feasible. It's not always feasible, or it's very expensive to accomplish. And also in some places, connection is not always available, or it's really expensive. And what's more, like privacy concerns. So there's also a need that we can actually, there's a need to train the DNN model on device without label or with like a minimum number of labels. All right. So first, let me go into the first part, the inference without battery. So energy harvesting is not something new. People have been doing this like RF, vibration. These are all example like embedded systems that powered by energy harvesting. For example, like with a dragonfly, a insect, a bird, or like use these coils to harvest the energy from a radio frequency, or even on your body. There are a lot of energy that you can harvest. So the model we are envisioning is that if we can have energy harvested from the environment and run a deeper neural network model on these embedded systems, usually either this system is going to make a decision by themselves, or this system can be used to wake up a larger device which is powered by battery. But if we are working in this way, then basically this little device that's powered by energy harvesting can be constantly looking out for events of interest. And only if it detects something it's interested, it's going to wake up, this larger device. So the larger device can be asleep for most of the time of course, to conserve energy. So that's so either the sensor can work by itself, or it can be used to wake up a larger device. Right. So when the sensor is working under energy harvesting, it's quite different from the system that powered by battery. The main difference is that the energy we harvest from the environment, usually it's weak, it's intermittent. So this figure on this chart, I'm just trying to show that on the x-axis, it's the time domain. On the y-axis, it's showing the percentage of computation progress. So what I'm trying to show here is that and this line actually shows the power trace, high and low. And when it's low, it means that we lose power. So what I'm trying to show here is that like when you are doing a computation, when you have power, you can make in progress. But if you lose the power, then you are going to reset. So you are not going to you are going to just lose everything, and you have to start from scratch. Okay, and of course, something we can do is that we can do duty cycling, right? We can save up some of the energy, and only when we have a large amount of energy, then we will start to do the actual work. But even we are doing this, it's still like there is a limit of how much progress we can make. So, um, so our lab we have previously we developed something called non-volatile memory-based system. So basically, what we did is that we are trying to save the progress when we lose the power, and when the power comes back again, we are going to resume the progress. So in this way, we can actually making arbitrarily long progress. But while so here I'm trying to show you a video of what we were able to achieve before. So you can see on this device, we were using solar panel to power this little device. And you can see that on the screen, it's showing the progress for faster Fourier transform. You can see that whenever you turn off the light, the screen goes off. But when you turn back on the light, you can see that the progress is actually not interrupted. So the progress actually will keep going. So you can see that this is just a solar panel powered system. Okay. So this was designed for faster Fourier transform. And when we were thinking of this deep neural network, so the most intuitive way we came up with is like, can we do something similar? Okay. And it turns out, yes, we can. So actually, when we thought about this, actually, we find out actually someone else already did this. So this is a ASPLOS paper published 2019. So what they did basically is doing this. So whenever it is a power failure, they are going to save the intermediate results of all these convolution operations. And when the power comes back again, they are going to doing the resume from where it was left and continue. So in this way, they can finish the deep neural network computation. But when we think about this problem again, we think that this is not the best solution to address this problem. The reason is this. So when we are trying to use the little sensor to detect some event of interest, the problem is that if we are doing this saving and resuming, by the time we finish the computation of the whole neural network, the events that we are interested might has already passed like a long time ago, because we do not know actually how much energy we can get from the environment, and we don't know when the power will come back again. So it's very likely, like say, if we are interested in seeing a pedestrian like walking by, but by the time we finish the computation, the pedestrian may already like walked far away. So we can't really do anything about that. All right. So in order to solve this problem, we came up with this event-triggered intermittent inference. So what that means is that instead of using a traditional deep neural network, we came up with this multi-exit deep neural network. So what that means is that this network has multiple exits. It has exit 1, 2, and 3. Okay, and the reason, you should see the reason shortly. So the main reason that we designed the network in this way is that we want the system to be able to take an exit whenever the power is running out. So for example, when the the deeper neural network is running here, and you detect that you are going to lose power soon, then it can use the remaining power to finish the computation and take the exit right away. So in this way, we can immediately make a decision. But please note that because you are using a shallower network, so the decision might not be as accurate as the third exit, but still you have a decision. It's still better than nothing. So that's our main philosophy. All right. So, but in order to fit this kind of network onto microcontrollers, there are some challenges: large model size versus small storage, high computation cost versus low available energy. And if you look at this network, you can see that when we are adding multiple exits, we are actually increase the size of the model. So therefore we need to do some compression. And also for this kind of model to work, we need to decide to select which exit for each event to achieve a high average accuracy and a low average latency in the long term. Okay, so in order to address these challenges, we are making the following contributions. So first, of course, we came up with this intermittent inference model. Second, we proposed a power chase aware compression algorithm. So we compress multi-exits to fit to microcontroller. So you may ask, what is the difference between this multi-exit network compression versus traditional network compression? Because pruning and quantization has been proposed for a long time, right? So what are the main differences? So the main thing we observed is that if we use traditional network compression algorithms, we find that not just like the final exit will have a accuracy drop. So the first exit actually will have a much larger accuracy drop because the traditional compression algorithms only consider to preserve the accuracy from the last exit, but did not consider the early exits. So they will have a larger accuracy drop. Okay, and also we need to propose a runtime adaptation technique to dynamically select which exit to take. For example, so when at this moment, so the x-axis is the time. At this moment, if there's event happen, and then if we do have enough energy, we might need to decide that we are going to run all the way to exit 3. But if like at this moment, we only have a smaller amount of energy, then we might need to decide that we are going to select exit 1. Okay, so that these kind of decisions we need to make here. So in total, like we have all these 3 contributions. So the first, the compression algorithm is done during the offline time, during the compile time. So basically, the network is going through this non-uniform compression, and then after compression, we are going to deploy that to the device, and the runtime exit selection is going to run during the runtime. Okay, and the network compression, we adopt both pruning and quantization. And during the runtime exit selection algorithm, we are trying to maximize the average accuracy of all events in the long term. So let's see, let's look at them each one by one. So first, this power trace aware network compression algorithm. So we are using a reinforcement learning based framework, and we have 2 agents, and they are trying to determine how to prune and quantize this network. So for the pruning, we are only, in this work, we are only looking at a channel level pruning. And for quantization, we look at quantization for both inputs and the weights, okay? And so basically, these 2 agents are going to generate the pruning ratio for each layer as well as the bit width for each layer. And then we are going to apply this to the network. And after you apply to the network, we have this exit guided reward calculation. So in this reward calculation, we are going to take the energy harvesting power chase and the event distribution into consideration. Okay, and then basically what we are saying here is that under this kind of event distribution and energy harvest power chase, what is the network that's going to give you the most accuracy? And this is going to this is search process going over and over again until it converges. So after we find a good compression and for the multi-exit neural network, we are going to deploy them onto devices. And during the runtime, we need to make two decisions when the event happens. So which exit to select, as well as if we select this exit, do we need to, are we confident about this decision? If not, should we proceed to the next exit for high accuracy? So we are using lookup tables to make the decisions. And since the energy harvesting environment is dynamic, we actually use a Q-learning based method to update the lookup table dynamically. So that the goal is to achieve a higher average accuracy in the long run, right? And this is the way we are formulating the Q-learning problem. So this is the experimental results. So for the blue bar shows the preserve ratio for each different layers, and the orange line shows the quantization bits for different layers. So you can see that the pruning and quantize, they are not uniform. They are non-uniform, and it's especially tailored for this kind of multi-exit neural network. So this figure shows the interesting events per millijoule. So basically, we are measuring like for our approach compared to existing approaches, how many, with the same amount of energy, how many interesting events that we can detect. And you can see that our method can detect higher higher number of events than other methods. And this one shows the flop reduction. So while the first half shows the flop reduction for each layer, and the second half shows the flop reduction of our method compared with existing methods. And this one shows the runtime exit selection. So this one shows the shows that like if we are just using a static lookup table, it may perform well like at the very beginning, but after a couple of learning episodes, the Q-learning methods can achieve a higher accuracy. Okay, and this one basically shows out of all these exits we are taking, how many exits, how many decisions are made by exit 1, how many are made by exit 2, and how many are made by exit 3. Okay, so and you can just give you, so not surprisingly, a lot of decisions are actually made by the first exit. This just shows you a prototype we made. So it's powered by solar panel, and you can actually see that there's a LED light here is a red and here's a blue. In this demo, we actually demoed like just a face recognition. So when we detect a human face, then we are going to turn the LED light to blue. So that's just a very simple demonstration. All right, so learning without labels. So after the second question we are trying to answer is that like once you deploy the model, can we improve the model adaptation? Well, can we improve the model when you see new data? So the intuition behind this is that like, well, so this is a robot, and let's assume it's R2-D2 from Star Wars, and let's assume that it has a deep neural network on its device. So, well, it probably has already been trained to recognize all these enemies, right? But then what we are trying to answer is that like when you see a new enemy, can you learn that that's a new enemy? So that's kind of like the thing that we are trying to do, and there are a lot of need for this, right? So robots, drones, so to kind of like to improve the accuracy basically. So and what's more, we want to achieve this with unsupervised or semi-supervised learning. So so self-supervised learning itself is not something new. So actually, the latest work on contrastive learning can achieve a very good results already. So let me give you just a little background on contrastive learning. So on contrastive learning, what we are doing is that like with the original image, we are going to do two data augmentation. So x2.xi and x2.j. So basically, what we are doing is that we are going to crop, resize, or flip, or we'll add some Gaussian noise onto this, and we are project this into the feature space. So what happens is that no matter how we are augmented this two image, they are still the same dog. So what that means is that like the feature we're extracting from these two images, they should agree with each other because both of them are dog, right? So if we use this to maximize the agreement, we are going to train a good encoder. So in this way, we basically train a encoder without any label. So we don't need a label to indicate this is a dog, right? Because for any image, we can just do this and to ask the model to maximize the agreement. So by this way, we just learn how to extract feature, even though that we don't know what it is, but we know how to extract the features. So that's the main idea here. Okay. So and surprisingly, this kind of unsupervised learning with limited number of labels can achieve a very good performance. So you can see that SimClear, this is one type of contrastive learning, can achieve on par with supervised learning. The accuracy is very close to supervised learning, but there's a little catch here is that like for supervised learning, we only needed like 25 million parameters, but for SimClear, we actually need like a huge number of parameters. And of course, like these kind of training are all done offline, which means that they are done in the server. And all these images, even though they don't have label, they need to be balanced, which means that you probably need the same number of dogs and cats, even though you don't know what they are, but they should be, the data set should be evenly balanced. So when we are trying, so the most intuitive way to achieve our goal is, of course, is to apply contrastive learning onto the device, right? But just simply adopting contrastive learning onto device is not really that simple, because when the robot or when the device is seeing a new data, it sees a never-ending data stream. It's not a well-balanced data set, and you kind of like need to store them to learn, but we have limited storage and energy, so that prevents you from doing that. And also, all the data you are seeing, the streaming data, they are temporally correlated. It means that, well, for example, in the same 10 minutes, you probably seeing the same thing, right? So they are not evenly balanced. So they are not, they are non-RID, means that independent and identically distributed. There's no labels available for streaming data. So we need to select, there's a need to select the data and to learn without leveling the labels. Okay, so in this work, our contribution is that we developed a self-supervised on-device learning framework. We developed a contrastive learning score for data selection so that we don't need to store all the data to learn, but only to select the most representative data in the buffer for learning, right? So we also developed a lazy scoring for reduced computation overhead. So let's see what they are. So this is our proposed self-supervised on-device learning framework. So the new data, when we have a new data come in, we already have some data that's already maintained in a memory buffer. So we are going to combine them together and use this contrastive score to select the most representative data. And then we feed this representative data to the encoder, to train the encoder, and also after you train the encoder, we will still need a few labeled data to train the classifier. Okay, so we still need a few labeled data, but we don't need to label everything. The majority of data does not need to be labeled. So then the question is, how do we define this contrastive score to know what is the most representative data, or what is the data we really need to learn, and what data we don't really need to learn from? Okay, so the idea of the contrastive score is this. So for all this new data and the data in the buffer, we are going to do a simple flip. So you can see that we flipped orientation of all the images, okay? And then we have two image xi and xi plus, and we are going to feed these two image to the encoder, and of course get its representation vector, and we calculate this contrastive score in the projected representation space. And the idea is this: if this, for example, this black cat and this black cat, and it's a flipped image, if the score is very small, means that like the model can recognize that they are the same thing. If the model can recognize that they are the same thing, that means that the model has already learned well to how to extract the feature from these two cats. Well, this cat. And if this, for example, like this is two dogs, if you just simply flip the image, then the model immediately think they are two dogs. Then it means that the model hasn't really learned this image really well, right? So that's kind of the main idea. So if that's the case, we are going to delete this cat because the model has already learned this really well. And we are going to keep this because the model hasn't learned the dog really well. So the contrastive score is defined as this. And there are some theoretical analysis on our paper, which is a paper published in last year's DAC. So if you are interested, you are welcome to check this out. So once we have this contrastive score, we also made another observation, is that like in each iteration of data replacement, most of the data in the buffer are preserved, while most of the new data are actually directly dropped. So the score of one data only slightly change across several adjacent iterations. So therefore, based on this observation, what we are doing is that for data that's already in the buffer, its score is updated every t iterations instead of in every iteration, and we are effectively reduce the computation overhead of the contrastive score to about 1/t. All right, so this is experiment results. So you can see that contrastive score can reduce the contrastive score based data replacement can actually beat all other state-of-the-art methods. And also, this is another comparison with different data sets. And here also we are trying to show that we are able to improve the score, and we can learn faster and achieve higher accuracy. We test our algorithm with CIFAR10, ImageNet 100, as well as two other data sets, right? And the lazy scoring can also like reduce the computation overhead. And then more interestingly, we see that, so we tested different lazy scoring interval. So most interestingly, we find that like actually interval t equals to 50 actually can give you the highest accuracy, actually even higher than disabling the lazy scoring. Right. So this is just like a part of our work, and there are still a lot of other questions that remain unanswered. For example, like for the we still need like a limited number of images to be labeled. And how do we select what data to be labeled and when to be labeled? So those are some of the questions that that still not answered. So right now we're just using random selection, but while it performs really well actually, but we are trying to do some theoretical analysis to see what is the best strategy to do the data selection for labeling. Okay. So that concludes like two of my main works. There are still like some of other related works. For example, we worked with a medical company to do this ICD and machine learning kind of research. Um, so ICD, it's called implantable cardioverter defibrillator. So basically, is that like if you have a heart arrhythmia, you can deliver electric shock to the to the heart to get it back to normal rhythm. So there are existing methods, signal processing based methods. But so the company, while we are all interested in see how machine learning can help, so we developed some model and especially doing some personalization. Um, so in traditional ICD devices, like all these parameters need to be fine-tuned by doctor. So in this work, we are trying to ask the deep neural network to personalize based on the patient's data instead of like relying on the doctor. Okay, so this is results, and there are several papers published. And again, if you are interested, feel free to check that out. And we have some other hardware, software, co-design work as well. And recently we received like one Best Paper award and several Best Paper nominations as well. All right, so future work. So there are still a lot of work to be done. For example, something called multimodality. So for example, learning. For example, like if you see this enemy that you know is enemy, but if you see this enemy and also hear like gunshots, then you know that wow, it's I'm in danger and I should run, right? So stuff like that. And also, if this robot like learns this enemy and another robot like learns other enemy images, can they like communicate with each other, especially without any supervision? So this federated learning without any supervision. I think those are interesting problem as well. Still, I think there's still a lot of problems to be solved. This is actually a document released like 2 years ago by CCC, Computing Community Consortium. It's a 20-year community roadmap for AI research in the US. And it's a really nice document. If you are interested, really encourage you to read it and give you really nice vision on what to be solved. And I think there are still a lot of problems to be solved. And there are a lot of interesting things to be done. Okay, I want to thank my students. They are doing all the hard work. I want to thank my sponsors that they are paying for all the students. And I'm happy to take any questions you might have.
Thank you, Dr. Hu. I have a question about the multi-exit neural networks. Do you know of any industry applications that are being used now, or are they still primarily constrained to academia?
So right now, I think like we are kind of like the first ones that, well, multi-axis neural network itself actually it's not. People has already proposed that like for compression purposes, but how to use this for like this kind of intermittent inference is something new, and it's something we developed. We are I don't know anyone is using it, but actually we are interested in commercialize this.
Yeah. Okay, cool. And then do you have code that's open sourced?
The code is open source. So right now, well, right now it is not. Actually, we are working on that. Like we plan to release this like on GitHub.
Okay. All right. I might follow up with the email and see if you could share your repository.
Sure. Yeah.
Thank you.
Yeah, I think this is really interesting, and we do have some interest in like doing commercialization for this. Any other questions? Okay, so I guess like if you don't have any questions, I guess that's all for this session. And thank you very much for your attending.
Thank you.